All right, let's jump right in. Welcome to this explainer on unlocking the triangle. I am absolutely thrilled you're here today because we're going to take some classic geometry and transform it into something you can actually visualize and apply. Imagine we're stepping into a really dynamic, brightly lit classroom. Today, we're not just staring at static shapes. We are going to demystify the internal, hidden balancing acts of triangles. Trust me, by the time we finish, you're going to look at the structures around you in a completely different way. So, I want to hook you right away with a real-world physics puzzle. Picture this. You cut a perfect triangle out of a really stiff piece of cardboard. Now, if you wanted to balance that cardboard triangle perfectly flat on the very tip of a pencil, where exactly would you place that pencil? You can't just guess or the whole thing just immediately tips over, right? You need the exact center of mass. Well, it turns out our upcoming geometry lesson on medians is actually the ultimate foolproof tool to solve this exact physical puzzle. It's a beautifully cumulative journey where every single step builds directly on the last. Okay, let's lay out our roadmap for today. First, we'll meet the triangle's median. Second, finding the geometric center. Third, the secret ratio rule. Fourth, right-angled triangle rules. And finally, the converse detective theorem. Let's start with section 1, meet the triangle's median. Before we can balance anything, we really need to know what tools we're working with inside our geometric shape. So here's our essential definition. A median of a triangle is a very specific line segment. You just start your pen at one vertex, one of the corners of the triangle, and you draw a straight line directly across the shape to the exact midpoint of the opposite side. It literally cuts that opposite side into two perfectly equal halves. And since every triangle has 3 vertices and 3 sides, it naturally follows that every single triangle out there has exactly 3 of these special median lines waiting to be drawn. Moving right along to section 2, finding the geometric center. So what actually happens when we take a single triangle and draw all 3 of its medians at exactly the same time? Well, this brilliantly illustrates our first major breakthrough. Theorem 4.1 states that the medians of a triangle are concurrent. Now, concurrent is really just a fancy mathematical way of saying they all crash into each other at the exact same location. No matter what kind of crazy, lopsided, scalene triangle you draw, if you draw the 3 medians perfectly, they will always intersect at one single point of concurrency. And we're going to label that magical intersection point M. Now, this point M is kind of like a geometric celebrity. And like any celebrity, it goes by a few different names depending on who you happen to be asking. Mathematicians usually call it the point of concurrency or the centroid. If you're talking to an architect, it's the geometric center. But in physics, it's called the equilibrium point. And hey, that perfectly answers our opening question. If you place your pencil tip exactly on the centroid, your cardboard triangle will balance flawlessly. But the centroid isn't just a physical balancing point. It actually holds a deeply ingrained mathematical secret. Which brings us to section 3, the secret ratio rule. See, the centroid doesn't just sit on those median lines. It actively slices them up according to a very strict rule. But, and this is absolutely crucial, you have to pay close attention to where you start measuring. If you start from the corner, the vertex, the centroid divides that median line in a 2-to-1 ratio. But if you measure from the flat opposite side, the base, it's a 1-to-2 ratio. The absolute easiest way to remember this? Just remember that the longer segment of the median is always the part attached to the vertex. Let's look at the visual proof of Theorem 4-2 to make this super concrete. Check out the distance from the centroid M down to the base at point E. The measurement there tells us ME is 4 centimeters. Because of our 2-to-1 rule from the vertex, the distance from M back up to the vertex C has to be exactly double that. And sure enough, MC is 8 centimeters. It's completely consistent. The segment touching the corner is always twice as long as the segment touching the flat side. Now, what's really fascinating here is how we can frame this exact same rule from the perspective of fractions. If the segment from the base to the centroid is a 1-to-2 ratio compared to the rest of the line, that means the short piece is exactly 1/3 of the total median's length, which means the longer piece from the vertex is 2/3 of the total length. Knowing this simple fractional breakdown, it's a real game changer because it makes solving complex geometry puzzles incredibly fast. Let's actually put this into practice and solve a problem together, just like we're working it out on a whiteboard. Let's find the perimeter of that tiny internal triangle EMD. Step 1. We see medians CD and BE intersect right at our centroid M. Step 2, we use our secret ratio rule. We know the whole line BM is 6 centimeters, so the shorter piece from the base, EM, has to be half of that, 3 centimeters. We know the whole median CD is 12 centimeters, so the short piece MD is 1/3 of the total, 4 centimeters. Step 3, because E and D are midpoints, the line connecting them, ED, is exactly half of the big base CB, making it 6.5 centimeters. Finally, step 4, just add up our 3 new sides. 3 plus 4 plus 6.5. Boom! The perimeter is 13.5 centimeters. See how beautifully that all just clicks together? So, the really important takeaway here is that this ratio rule is actually a two-way street. The source material outlines a corollary here. It basically tells us that if you're examining a median line and you happen to find a random point on it that divides the line into a perfect 2-to-1 ratio from the vertex, well, congratulations, you have just found the centroid. You don't even need to bother drawing the other two medians to prove it. The math literally guarantees it. Up until now, these rules have applied to every single type of triangle. But what if we look at a very specific, very famous type of triangle? That brings us to Section 4, right-angled triangle rules. Things get really, really interesting when we introduce a perfect 90-degree corner. Theorem 4.3 reveals a highly specialized rule. If you have a right-angled triangle and you draw a median originating specifically from that 90-degree right angle down to the opposite side, which, as you know, is called the hypotenuse, the length of that median will be exactly perfectly equal to half the length of the hypotenuse. It is such an incredibly elegant relationship between the angle and the opposite side's geometry. And let's see how this builds into our final and, frankly, my favorite concept for today. Section 5, the converse detected theorem. So consider Theorem 4-3. That's a direct rule. If you know for a fact the angle is 90 degrees, you instantly know the median is half the hypotenuse. But now compare that with the converse of the theorem. This is straight-up reverse engineering. This rule says that if you draw a median, and you notice its length happens to be exactly half the length of the opposite side, then the angle you started from absolutely must be exactly 90 degrees. No exceptions. Let me break down exactly why this basically makes you a geometric detective. Imagine you're inspecting a triangle, but you don't have a protractor to measure any of the angles. Step 1, you just measure the median. Step 2, you measure the opposite side. Step 3, do the quick math. Is the median exactly half of that side? If the answer is yes, then step 4, you have conclusively 100% proven that the starting angle is 90 degrees. You deduced a hidden fact about the triangle's angles using only the lengths of its lines. It's just an unbelievably powerful logical tool. We have covered a lot of ground today, all the way from the basic median up to reverse engineering right angles. But I want to leave you with a thought to really chew on. Today, we absolutely mastered the 2D plane. We learned how centroids balance flat shapes flawlessly. But if these strict, uncompromising mathematical balancing rules govern the two-dimensional world so perfectly, how might these exact same principles of the centroid scale up to hold our real three-dimensional world together? Think about it. How do they apply to balancing massive 3D pyramids, suspension bridges, or the engineering marvels you drive past every single day? Keep looking for the math in the world around you, because I promise you, it is holding everything together in perfect balance. Thanks so much for exploring this with me today.